Unit 9.2 Magnetism. Problems continued from the class on 4.8.13. Looking at the right-hand rule for the particle and the wire. Part of the problem with this is that we have a B field that's actually changing, and so with this, the right-hand rule is a little bit tricky. So what we have to do is take a snapshot of the B field just at the point of the particle. So we can see in the top picture A is that as the particle is moving against velocity or against the current, is that at that snapshot the B field is actually pointing directly down. So remember, we do the right-hand rule for a positive particle. So if we're working with an electron, we're going to do the right-hand rule and then reverse our result. So the picture is actually showing the correct result. Now let's figure it out using the right-hand rule. So using your right hand, point your index finger in the direction of the velocity of the charge. Then you're going to flip your hand and bend your index ring and pinky fingers down in the direction of the B field. Again, snapshot. And what will end up happening is that your palm's facing down and your thumb is pointing towards you. But since it's an electron, we then flip it and we see that the force of the on the electron is actually going towards the wire in scenario A. Second scenario, when the velocity is going towards the wire, we can then point our middle ring and pinky fingers down. Again, snapshot of the circular B field, and your thumb, the force, is going to be pointing to the left. But again, since it's a electron, we're going to flip it and it's going to go to the right. So that's how we will figure out the interactions between the charge and a circular B field. Is again, take a snapshot of the B field, not try to do the whole B field with your fingers. Where we left off was talking about the attractive and repulsive forces on wires carrying a current. If currents are going in the same direction, what ends up happening is that you have a B field going in and out of the paper for the two wires, and that creates an attractive force. When we have two wires where we have current going one direction and in the opposite direction, it's going to be a repulsive force. One wire having a mag field going into the paper and one going out of the paper is going to be attractive. When they match, either both going out of the paper or both going into the paper, they're going to be repulsive. Again, think about this, the in and out of the paper like north and south of a magnet. Let's look at the problem. The cables that connect a starting motor with a car with its battery are 10 millimeters apart for a distance of 40 centimeters. Find the forces between the cables when the current is 300 amperes. Nothing in this problem talks about the direction of current, so all we're going to be able to find is the magnitude of the force on the two wires. We don't know whether it's going to be attractive or whether it's going to be repulsive until we know direction of current. So magnitude only we'll be solving for. And for our equation, we're going to use F is equal to mu naught times the current squared divided by 2 pi r, r being the radius or the distance between the two wires, and then L being the distance of the wires that we're looking at. Mu naught, remember, is a constant that's going to be given to you on your formula sheet, and that's 4 pi times 10 to the negative 7th Tesla meters per ampere. When we use mu naught, we have to make sure that our currents are converted to amperes and our distances are converted to meters. Often with these circuit problems, though, remember that you're going to be dealing with very small distances, so don't get tripped up by that. The current was already in the correct format, 300 amperes, and R is 10 millimeters, we convert, and 40 centimeters, again, we convert to meters. So then we take our information, plug it in, mu naught times 300 amperes squared divided by 2 pi times 0.001 meters. We take that answer, multiply that by 0.4, and we get our final answer of 72 0.72 newtons. Again, since this problem does not say direction of the current, the attractive or repulsive nature of this force cannot be determined.